Let's move to the second part of the day here of our presentation. And I'm going to drive this with a fellow who came over and had a little discussion with me. And there were a couple things I wanted to clarify because I think they're pertinent. Let's go with the first one. And that's something that the mathematicians do all the time. They talk about instantaneous. What the hell is instantaneous? Instantaneous is a word that belongs in ordinary speech, never in physics. I don't know about math. We don't care about math, but it's not even applicable to math because math only deals with motion, and instantaneous is, the Mona Lisa smiling and frowning in the same picture. That's what it is. So here it is. This is what we have. His fellow says, the torsion of the rope is quicker than c. Velocity of light, right? 300,000 kilometers per second. Possibly instantaneous. And now for that we have a tool we call the universal movie, which destroys all of special relativity especially, but mathematical physics in general, because every atom in the universe is in a single frame. It's a 3D frame. It's God's film, right? So God takes a picture of the universe, every particle wherever it is, and that's a snapshot, right? And he stops the universe. Nothing moves. The next motion, the next frame of the film, every atom in the universe is now at a new location. A gazillionth of whatever distance from where it was before. So suddenly it went from here to there, right? So every frame has only every atom in the universe. There's no time. You want time, you need to see the whole film, right? Or at least 2 frames of the film. But in the single frame, all you have is location. Okay, so we have the universal movie. Each frame only has every atom in the universe at a location with respect to all others. Okay, and so we have instantaneous motion, and the problem is that in order to have instantaneous motion, you would have to have all the particles in the universe in one frame, and at the same time, every single particle in the universe also distant from that location to where it was going to be moving next. So you have two frames superimposed one on top of the other. That's what instantaneous means. Okay, you can't have that. Big instantaneous is a word that involves time, motion, right? For that you need at least 2 frames. And here, let me give you an example. And an example is worth 1,000,000 words. Okay, here it is. Here you have the universal movie. Okay, and we're going to talk about weight. Okay, and the mathematicians, they say that gravitational waves, or whatever they call them, can't travel faster than the speed of light, because Einstein proved so apparently in special relativity that nothing can travel faster than light, right? And so gravity cannot propagate faster than light. That's what they say. And so they have this explanation where, the sun collapses or disappears, and it takes 8 minutes for that signal to reach the Earth. That's one of them, right? But the question is, here we prove them wrong. Okay, if you talk about proof, here you have proof. Okay, here you have all the atoms in the universe, and you have you. Okay, that's you there. Okay, you're standing still, completely still. We take a snapshot of everything there, right? And now every atom in the universe is going to move a gazillionth of an inch. I made it a little bigger there. I put 2 little dots so that you can see that the guy moved, right? But just consider that the minimum motion possible, the next frame in the film in the universal movie. Okay, so what happens? When you move from that first frame where you have 100 kilograms, you move to the second one, your weight changes instantaneously. We're going to talk about instantaneous. What changes is your weight. That changes immediately. As soon as you take a step, your weight changes automatically. Okay, you don't weigh the same thing because weight is location specific. You change your distance with respect to the Earth, your weight changes instantaneously. Okay, so that's the only notion of instantaneous you can use in there. You need 2 frames, but what changes instantaneously, you could say, without any light traveling at the speed of light, that's 300,000 kilometers per second. No, it's not going to wait. The next frame in the film, you'll already change your weight. Okay, so keep that in mind. Weight is location specific. You change your location, you instantly change your weight by whatever gazillionth of a gram or whatever. It doesn't matter, but you change your weight. That's how it works. Okay, so weight changes instantaneously, and that's what we use. We use the universal movie to show that. And let me show you a few more here, so that you can get a good picture of how idiotic all these mathematicians are across the world in every university on the planet. Not one of them survives. Okay, they're all been talking nonsense and created this universe of black holes and dark energy and dark matter and Big Bang and particles at two places at once and tachyons that come from the past and who knows what from the future. Right? Now they have all this nonsense that they created. None of it survives. It's all garbage. Okay, so here we have, here's the second question this fellow asked, and this goes to show, how people are thinking. They're thinking in mathematical terms. And this fellow says, your assumption is based on an experiment. You simply are using an experiment to affirm that the rope's velocity is c, okay, 300,000 kilometers per second. And no, when I came up with a rope model, I didn't use, speed at all. I did a lot of math. I did tons of math for about a year, a waste of time, because I kept doing math and math and math, thinking I was going to come up with a rope with a solution to gravity and light and so on. And it helped not a bit. Math served no purpose for what I was looking for. I was looking for an explanation. And yeah, you won't find it with math or with experiments. They're worthless. Okay, so here we have my answer to him. Said, my assumption has nothing to do with speed, okay, because I didn't look at the speed of light at all. I didn't care about speed. I wanted to find qualitative answers. I didn't start with speed to come up with a rope model of light and gravity. I didn't use speed at all or pay any attention to this parameter. And my assumption has nothing at all to do with measurement. Okay, we don't use measurement in science. Okay, that's math. They like to measure. They like to do experiments. Go ahead, knock yourself out. When you come to the conference, we need an explanation. That's what we want. We want you to tell me why, what caused something to happen. And you can't do that with experiments. You can't just do an experiment like Faraday used to do at the Royal Society. He would come and do an experiment and say, wow, look, and a magnet attracts another. Great. So how did it do it? That's what we want to know. Don't show me the magic trick. Tell me how it was done. You cut the lady in half and say, see, I cut the lady in half. Yeah. Tell me how you did the trick. That's what we want to know. Okay. In physics, we have no use for measurement, speed, time, distance traveled, or math. That was my answer. And again, this comes from all these mathematical physicists from the 17th century. Here you have them again one more time. That's who they were. Some of them. This is just 10 of them from that age. There were a lot more. They were all doing experiments, of different kinds, trying to figure out how this universe works. I mean, you can do any experiment you like in your dark basement. We don't care. When you come to the conference, we need for you to explain a mechanism. That's not philosophy. That's called physics. Okay. And so let's go through this. Let me show you this. We have a series of equations there. Some of the equations that they have no answers to, okay? One is that first one I talked about the other day, c, little c, constant of velocity of light equal frequency times wavelength, right? And that's easily solved under the rope model, whereas mathematical physics has no idea why that's the case, okay? Here it is. Okay, here you have the electromagnetic wave. We're going to replace that with a rope. A wave is a bunch of vectors that are moving, totally irrational, moves in one direction only. In this case, I'm going to move it to, well, it doesn't matter. Moves one way or the other. Rope throws in place, throws in situ, goes nowhere. That's why it's so fast, because it's the torsion that thumps the atoms at the two ends. Okay, a rope connects any two atoms in the universe. All atoms are physically interconnected. Physically interconnected. But there you see the rope equation. And only the rope can model c equals frequency times wavelength. You have a rope, and here I always do my little trick with a rope. Okay, and if you torque it more, okay, for the same amount of rope, right? The links become shorter, and you have more links. Frequency, more links, right? Wavelength, link length, shorter, okay, and vice versa. So only a rope can explain the wave equation, which Maxwell has stamped, his name on it already. And here you have the second one there. Let me get rid of this one. Let's do the gravitational constant G, another thing that the mathematicians have no clue whatsoever about. And you can see why. Here you see, look, the force equals to G, like the gravitational constant G, mass 1, mass 2 divided by distance squared, right? Okay, we've known that. People say, well, Einstein replaced that with his field equation, and it doesn't matter. This is the one they use to send rockets to the moon. It works just fine within a certain range, okay? And for sending rockets to the moon, this is accurately enough. They do not use Einstein. They trashed Einstein completely. It's too difficult to deal with. Besides, you got to remember Einstein's equation. If we're going to give you an example, right? What does Einstein's equation do? When you figure it out, you calculate everything. What it does is tell you, like, take a planet like Mercury. It tells you what a point mass. You take all the mass of Mercury, you point it into a point. You put it into a point right at the center. That's the center of mass of Mercury. And what it tells you is what that point mass, what it describes. How it moves around the sun. In other words, how it bends space-time. Or how it what the itinerary is. It gives this Rosetta-type pattern. Where it shifts its perihelion every so often. Okay, so that's all the equation really does. And they say, oh, it's great, it's better than Newton's. Absolute nonsense. It's not nonsense because they changed Newton's irrational nonsense, which was particles, and they replaced it with bigger nonsense, which is the warping of number lines, which they call dimensions or coordinates or something like that, No, they're number lines. Let's get it right. There are no dimensions, coordinates, or vectors. You have depth, breadth, and elevation. Those are vectors. Okay, 3 vectors. There's only 3 possibilities that you can move perpendicular to each other. We call those vectors in physics. Mathematical physics doesn't use any of that. What they use is number lines. They want quantification. That's all they do. So they don't have dimensions, coordinates, or vectors. But here we have it. We have the force equals gravitational constant G, mass divided distance squared. And we're going to look at this gravitational constant G, okay? And never have they found an explanation. What is that? See, you look at the units there, and what do they mean? What do they represent? That's what we're trying to figure out, right? So you see newtons there, the N for Newton, meter squared divided by kilogram squared. And you take that Newton, and it's equal to kilogram meter divided by second squared, okay? I'm going to put that in the next frame. You're going to see the whole thing. And then finally, you have the E equals mc², another famous equation, okay? Let's see what all these represent from a physical point of view. That's what we want to understand. What does this mean? That's it. Let's go with the gravitational constant G. Here it is. Here, put it up here. Okay, here we have it. Okay, so we have the force equals GMMM divided by distance squared. What is the G? Well, the G is equal to 667 newtons, meter squared, kilogram squared. What is a newton? Kilogram meter over second squared. So far, so good. We're going to replace the M with the kilogram meter over second squared, that little box there on the second equation there, right? And so now we have G is equal to that number, kilogram meter squared over second squared, kilogram squared. What does all that mean? What are we talking about? What kind of unit is that? And right at the bottom, we synthesize, and that's usually what they use. They use meter cubed over second squared kilogram. That's what it is. Okay, so if you synthesize that, you end up with that box on the bottom. So far, so good. Are you following me? Okay, so that's how we got there. Okay, I just want to go through that so that you can see how we got to that number at the bottom. Okay, so now we're going to replace this now with something else, okay? We're going to put that same thing, G equals, right, kilogram meter over second squared, which is the Newton, meter squared, kilogram squared. Okay, so far so good. That's what we had in the previous frame, okay? And now what we're going to do with this, you see I'm multiplying times 1 in red there, right? We're going to replace that 1 something the mathematicians never do. They like to synthesize, and here they had to go in the opposite direction in order to understand what they were doing. And then we put 10 to the 16 kilograms over 10 to the 16 kilograms. Hopefully that's a 1, mathematically speaking, right? So we're multiplying that whole thing times 1, 1016 over 1016. Okay, so far so good. If we synthesize all that, what we end up is the mass of the hydrogen atom, which is 1.67 over 10 to the 27th kilograms, times 9 times 10 to the 16th meters squared second squared, which is the velocity of light, okay, squared. And so we have now an understanding. What does G represent? Well, it has that mass of the hydrogen atom and the velocity of light squared. Okay, that's what it is. That's what it represents. And those who want to find out what 0.44 meters over kilogram squared means, that's for homework. We'll leave that for homework, okay? It's in the book, so whoever wants to buy the book, go find it there, okay? But otherwise, do the homework, try to figure it out on your own. Okay, so that's what's there. What does all that mean? Well, it means this. It means that every atom is simply a tiny heart. It's pumping, right? Boom, 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 boom. It's doing its quantum jump. Not a little bead that goes from energy level to energy level or from orbital to orbital. No, it's a sphere. It's a membrane that encapsulates a star. All the threads pulled out in every direction. And what it's doing its quantum jump, which is a ball that is becoming smaller and bigger. It's collapsing and expanding constantly. By doing so, it torques the rope, and that signal goes to every atom in the universe. And if you have something like the sun, which is very powerful, torques them at a higher rate, well, that's what comes to our eyes, to our world. Okay, so that's what it is. And so it's a tiny heart pumping torsion waves to every atom in the universe. And there you have the atom, okay, 1.67 times 10 to divided by 10 to the 27th kilogram, and you have the little c squared, which means that light travels in both directions from one atom to every atom in the universe, and every atom in the universe to our atom. That's what it means. That's what little c squared means physically. That's the physical interpretation, okay? And so now we arrive at our final one, which is E equals mc squared. What does that mean? E equals mc squared, energy equals mass times velocity of light squared. What could that possibly mean in physical terms? Okay, we have the same situation. We have every atom in the universe, or you can take a subset of that anywhere and just count all the atoms there, right? And each atom is 1.67 divided by 10 to the 27th kilogram, right? That's the weight of one atom, right? The mass of one atom. And what do we have? We have that atom is sending torsion waves through the rope to every atom in the universe, and everybody in the universe does the same thing to the rope. That's what the little c squared is, okay? So c squared just means one for all and all for one, like the three musketeers, okay? And that's what energy is. Energy is simply all the torsions of the universe. That's what it is. That's what energy is. It's just all the torsions in the universe. And if we're talking about every bit of matter, right? Mass, every atom in the universe times the velocity of light squared going back and forth. That's what it is. That's what E equals mc squared means in physical terms. And again, you can take any subset of that. You don't have to have the whole universe, all the matter in the universe. Just take any subset of that and the same thing applies. Energy will be the aggregate of all the torsions going along every rope in that system.